So we've dealt with conservation of mass. The next part is conservation of momentum. And that really goes back to Newton's second law. And now we write it maybe slightly differently than what you're used to. So in this case, Newton's second law will apply it for a material volume, so a volume element of the flow that follows the flow field with an area AT. And both the area and the volume can change, right? Remember that analogy of an infinitely stretchy balloon. So we'll think of momentum as rho times u, so the velocity times the mass. So this is essentially momentum per unit volume. And then you can write Newton's second law as d by dt over a volume Vt rho xt u of x and t dt dv, and that has to be the same as the forces. So this really is just ma essentially. It's the density integrated over the volume, and there's the velocity, and it's the time derivative of that. So this is analogous to ma here, and that ma has to be equal to f. So we have force terms on the right here. The first one is a body force term, and since really all the body forces we're considering here is gravity, we just write g. And so that has to be integrated over the volume plus, let me move this over here, plus the integral over the surface forces, let's call those F. And surface forces will also depend on the normal of the surface, and x and t dA. So these are F body force and surface force. So now on the left hand side here we can use Reynolds transport theorem. And turn that time derivative into an integral form, which will look like follows. So now we integrate over the volume, and it's d by dt rho u dv plus integral over a over the area rho u times u dot n dA. And that has to be equal to the force integrals, which is v rho g dv plus a f n dA. And this really is the integral form of the momentum balance for a material volume. For a material volume. And this is, as a side note, this is the momentum equivalent to mass conservation. And you remember mass conservation was simply the volume integral of d rho dt dv plus rho u dot n dA had to be 0. So now how do we turn this again from a integral form to a differential equation, to the differential form? And for that, I will refer you again to the Kundu book, see Kundu 4.4, and I'll spare you all the details here, but I encourage you to look at the proof of the derivation for the differential form. The differential equation that arises from the momentum balance is known as Cauchy's equation of motion. And I will give you the most concise form of Cauchy's equation here, which we'll write as rho times duj dt. So this really is just is just ma, is rho gj minus d by dxi tij, where tij is the stress tensor. And you might wonder, how did we get to suddenly the stress tensor if we started with the body force F, the surface force F, and you can look back a few chapters where we found that our Fi would be the normal Ni Tij. That's how we relate the surface forces to the stress tensors. So this is Cauchy's equation of motion. Now, it's a vector equation, so this really represents 3 equations. We also derived one more equation from mass conservation. That was the continuity equation. And we can get 2 more equations from thermodynamics, which I'll skip here. That means we have a total of 6 equations to describe our system. Now, how many unknowns do we have? Well, we don't necessarily know the flow field. So uj, that's 3 unknowns. That's typically what we want to solve for, right? The density is 1 unknown. And the stress field is also potentially unknown. And since that is a second order tensor, that represents up to 9 unknowns. So if we count that, we have 13 unknowns, but only 6 equations. So as it stands, our system is under constraint and we can't actually solve for our flow field and our stress field. The way you get around this is that we need to relate stresses to deformation or strain rates. And that will eliminate some of the unknowns associated with the stress tensor, because the strain rates, if you remember, are just typically functions like dui dxj. So if we can replace the tij by something that's just in terms of u, then we're eliminating some of the unknowns. And the way we relate stresses to strain rates is using a constitutive equation. And that's going to be our next chapter.